Okay, so hi everybody. So I'm Stéphane Clinchant from Naver Labs Europe. And today I'm going to give you an introduction to neural information retrieval. And so the outline of the presentation today would be first a brief introduction of myself and Naver and what I hope to cover in this lecture. Then we will talk about neural information retrieval model before the new era of pre-trained language models. Then I will spend some time talking about BERT and how we can use BERT for re-ranking. And in the last part, we will talk about how to learn a first stage ranker. So maybe all those names are not already are new to you, but they become clear. So we will see a different set of models, and hopefully at the end of the talk, you'll be able to know what those models means and what do they do and their strengths and weaknesses. Okay, so let's start with the introduction and a personal, I would say, motivation of a bit of a story of myself. You know, why did I study IR? So when I studied IR was not very popular. All the students were studying math and finance, basically. But I was really interested by math and language and how we can represent language, or how do people compute textual similarities, and also how do search engine works. And that was really, to me, like the key motivation to work in this field. And also, I think it's a very exciting field. Yeah. So now a bit of a disclaimer. So we see this empty board. So I haven't given a lecture for more than 10 years. So thanks, Nicola, for inviting me again to do this. But maybe some things are not clear, would be not clear for you, or too technical or too high level. So if you really have some questions, please do not hesitate to interrupt me and ask things. I would also appreciate your feedback at the end of this lecture to see what I need to adjust for future lecture. And then you see an ocean, a boat navigating some difficult sea conditions. And I think what I want to give you in this lecture is to give you some history on the models, to give you some good way to navigate the field and the ideas in information retrieval. Because you can find a lot of blogs about IR, you can find you can find a lot of resources on the web, but you won't get all the context and maybe all the history that you can get in this lecture. Okay, now a bit of words about Naver. So Naver is the 5th search engine in the world, and it's mostly a search engine based in South Korea, and it's the main search engine in South Korea. So all the population use Naver there. So about now 75% of web traffic or web search in South Korea goes to Naver. It has about 42 million users. So okay, Naver is an important search engine in Korea, but it's much more than a search engine. Like Google, it has a lot of applications such as maps, video, music streaming, shopping, and so on, recommender system. So it's a bit like the South Korean Google. Naver is also expanding in Southeast Asia with Japan or Thailand and these other countries. Okay, so Naver was a search engine, but it's not only a search engine, and it's doing a lot of research in other areas such as robotics, for instance. And now I will give you a short video of our research center, the activities we do, just to demonstrate like the various activity that Naver is looking at. Okay, so I guess that would be the most entertaining part of this lecture. Now let's talk about our search and recommendation team at Naver Labs Europe. So we are still a small team with only 8 people, including 3 PhD students. We have collaboration with some French university, but also the University of Amsterdam and the University of Waterloo. And yeah, we are working with some Korean team for their search engine as well. And yeah, so yeah, so that's our team. And basically, we look at 2 research challenges. The first one would be efficient architectures, something that we will cover actually in this lecture. And the second line of research would be accountability, making a search engine more transparent, fair, and diverse. And I think you had a lecture maybe last week or 2 weeks ago by Jean-Michel on this topic. Okay. Okay. So, as you know, search engine, is a field of computer science that started a long time ago, like in the 50s. And we had a lot of change in the technology and the model we use. And the most recent one was the one based on pretrained language model with BERT model. I don't know. Have people heard of BERT before? No. No? Okay. And so in 2019, it was really a big shift. And actually, when Google made BERT and when they changed their search engine, they claimed that this was the most important update in 5 years, basically. And after that, a lot of other search engines, such as Microsoft and Bing, also changed their models to use that new technology, basically. And since then, there has been like a race in doing bigger and bigger model. So you see here, it was end of 2019, you had the BERT model, you had the rightly already large model size in million or billion parameter. And since then, people have been doing bigger and bigger models to try to improve their performances. And Naver did also the same with their Korean language model. Yeah. And so I will explain a bit how this pre-trained language model can be used for search in this lecture. So, and as you may know, search engines are, they use basically two systems. There is a first stage ranker and a re-ranker. So you take a query and you use a first system such as BM25, which is very fast, which is very fast. And then you retrieve a set of 1,000 documents, basically. And once you have this 1,000 document, you feed that to a re-ranker. And this one is more costly to use more computation. Its goal is to find the optimal order to provide to the user. And so we will see how this new pre-trained language model, they can impact both the re-ranker or the first stage ranker. Excuse me. Okay, and so as I said, these pre-trained language models, they are really a game changer, both in natural language processing, computer vision, but also IR. There are some opportunities and challenges. And so on the left here, you see a plot from the TREC 2020 competition. So TREC is an IR competition that started in the 90s. And you see different systems, there are DCGs. What you see is that in blue are the traditional IR models based on BM25, pseudo-relevance feedback, and so on. And you see their performance in terms of NDCG at 10. Then in red, you add the old neural, not so old, the neural IR models, but already get some boost over the traditional approach. And well above all this approach, you get the method based on pre-trained language model. And so the goal of this lecture is to cover a bit this evolution in the field, to give some idea of the model that were developed for the neural approach to IR, and then see how the pre-trained language model can be used for search. Yeah. So I want basically to cover a bit what happened in the recent years, both in TREC and in search engine, so that you get the full story. Okay, so at the end, you will see how we can replace basically the re-ranker with a BERT pre-trained model, or we can also change the first stage ranker. Okay, so that's it for the introduction. I hope it was clear. So now let's move to the second part of the talk, which is neural information retrieval model. Before, actually, it's the year 2010 until 2018, basically. And yeah. Okay. So again, this is the classical anatomy of a search engine. We have the first retriever and the re-ranker. So at first, people were targeting to use neural net in place of a re-ranker. So instead of using, well, people use supervised machine learning algorithm to do that. And actually, if you look back in history, the first neural net that was used, well, one of the first neural net that was used in IR, it was done in 2005, well before the resurgence of neural net in artificial intelligence, I would say. And so in this paper in ICML 2005, basically the people propose a neural net to basically re-rank your top 1,000 document, okay? And after that, there was a lot of approach extending this, such as Lambda-MART and so on. I don't know if it was covered in other lectures. I'm not sure about this.
Not in the tape.
Not in detail. Okay. But yeah, so if you really want to understand what was done at that time, you could start from this paper about RankNet and Lambda-MART and so on. Anyway, so one important thing if you want to learn re-ranker, that was, and this was developed in those years, was to have proper ranking losses. So, and sorry. So if you want to use supervised machine learning, you could treat IR such as a classification problem, but it has a lot of limitation. So because what you want to do is to put the first relevant document on top of the list. And if you treat this as a classification problem, you're not sure that you will learn to correctly sort a list of documents. And this is why people have developed different family of ranking losses and different approaches. Again, Nicolas, I'm not sure that this was covered in a previous curriculum or previous lectures.
They have a curriculum on machine learning. They have a lectures on a course on machine learning. You can attend a course on deep learning,
okay.
But not specifically applied to AI.
Okay, so I don't think I will go on those details on those family of ranking losses, but there are, I would say, three important family or three important approaches if you want to learn a ranking system. The first one is the pointwise ranking loss. The second is the pairwise, and finally the one is the listwise. So the pointwise is really the simplest one. Is basically to treat your ranking problem as a classification problem. So you say basically all my relevant documents, they will belong to a class, and all my irrelevant documents will be another class, basically. And then you can use a cross entropy loss to do that, actually. But because this has a lot of limitation, people have been working on what is called the pairwise approach. And the goal here is to classify a pair of, or triplet of objects. So you have one query, one positive document, one negative document, and you want the score of the positive document to be higher than the score of the negative document. And so basically what you do is to treat, what you want to do is to classify pairs of documents. You want to say that, for instance, the document, this positive document and this negative document should be correctly ordered. And it means that the difference in score, it means that this score would be higher than the score of the negative one. And I'm sorry, maybe it's a bit confusing, but the goal is to classify pair of documents and to say which one is correctly ordered or not ordered. And so you do that basically by using a hinge loss and using the difference in score between both objects, difference in score between this document and the query. So okay, that's one approach to do that. There are many other losses and many other things, which you can find that online or in books, I think. The third approach is called the listwise ranking losses. And here the idea is to model the whole list that you want to re-rank. So let's say that you have a query and 100 documents. You want basically to better optimize the NDCG or the mean average precision. You want to really optimize the full ranking list because your loss is on the full list, and you can find approximation of this. So those listwise are usually more costly to optimize and to compute. And in the past, their benefit was not so clear to me. Anyway, I think that those three kinds of losses and family losses are important to know if you deal with learning to rank system, basically. Okay, so now I'm going to speak about something which will be, I would say, recurrent a bit in this talk, is that in IR there is some kind of debate or dispute, I would say, between on how the search and how the search model should work. And I would say that there are basically two approaches. We call the sparse model, which are term-based, such as BM25, and the dense models, such as these new pretrained language models, but also old models like latent semantic indexing that was developed in the 90s. So on the one side, you have some models, such as the dense model, that where you basically compute an embedding of documents in a low dimensional space. And once you have a representation of your document in this latent space, well, you do some dot product, and you do a dot product in this space. Implicitly capture on this low latent space. And so those approaches are called representation based. And a lot of old models, I would say, fall in this category, such as latent semantic indexing, or maybe topic models that were popular also at some point, or word embedding, if you have seen some lectures in NLP or in other machine learning courses. And then on the right side, you have the sparse model or the term-based approach, such as BM25 and all other variants, such as language models, divergence from randomness. And those model works basically by exact match, meaning that you do a dot product in a space of words. You have basically a bag of word representation of your objects, and you do your dot product on this. And so this I think this question about whether the models are doing more lexical match or more semantic matching has been around in the field for a long time. And this also will impact the way the models were developed. Okay. So in the past, sparse models were the best with BM25, and people were not able to learn a dense model that was actually better than the BM25 models. Now it's not the case anymore, and we will see. We will see that. So, as I said, there is a kind of a dichotomy between the representation-based model and the sparse model. And so, for the first neural IR model, they represent queries in document in a comment latent space. So basically, they were, okay, you had a model that projects this in a latent space, and then you would use a simple similarity function, such as Euclidean distance or cosine, to compute the distance between that. And so I have a question for you in the audience. So imagine that you were in 2015 or 17, maybe. So what function phi would you use to do this? Or maybe at your level, with the lectures that you have followed, you know, what kind of function would you use for phi?
Guys, any ideas? What can you do use for matching?
Use bag of words, vectors.
Sorry?
Like Boolean periods is the same.
No, I didn't understand. Can you repeat?
Like a Boolean match.
Boolean match, but here we have vectors in a vector space.
Mm-hmm.
Hence vectors, because the dimensions are way many less than.
Mm-hmm.
What can you use?
Maybe, can you hear me?
Yes.
Maybe as phi we could use some encoding of the sentences, and as f we could use some maybe cosine distance between the vectors.
Yes. Yes. Yes, that's the right answer. So people basically have used, for instance, CNNs and RNN at that time to do such kind of models or things based on word embedding. Okay. So okay, that's the main idea for representation-based model. But then this model, they were a bit criticized because they did not capture some classical IR principles, such as being able to do lexical matching, as we do with BM25 and term-based model. The role of inverse document frequency also was not clear. And the document length also, if you have a very long document, in BM25, you have some kind of normalization. Or is this normalization taken into account in the CNN or RNN or other kinds of models? And so the second family of model is called the interaction-based model. And here, the idea is not to embed your documents and query in a common latent space, but to work on their interaction. What do I mean by interaction? Is that for each word of the query and the document, you would compute some representation of that word. And then, so you will have a matrix of query term and document term. And then you will compute the similarity between the query term and the document term. And then you use this matrix as input to a neural net, for instance, and to decide whether it is a match that is relevant or irrelevant. So just to give an illustration, in this interaction-based model, instead of computing a representation of the query and the document which are independent from each other, you do a joint representation, such as this interaction matrix. So you would have a similarity between all pairs of query terms and document terms. And this matrix, you would feed that to a neural network model. And based on this, you would decide whether the query is relevant to the document. And this representation, I mean, there won't be a single representation for the query. Okay, and so actually, one of the paper that put forward the argument of interaction, this is representation-based model, was this model called DRMM that was published in 2016. And they were arguing for the interaction-based model, basically. They were saying, okay, if we do a representation-based approach, we have many limitations. And so, what they say in this paper, basically, if you want to have a fine-grained mechanism, it's more effective to count the word-level translation instead of just doing an average of things and doing a dot product on those things. Okay, so now let me discuss how it works actually, this model. So here you have a query term, the circles are query term, and then you have document terms in circles. The model assumes that you add some word embeddings, such as word2vec, and they were fixed at the beginning. Okay, so you are not learning those embeddings. So it's not an end-to-end model. And so once you have this word embedding, you would compute a cosine similarity between these different words in the query in the document. And so this cosine with similarity would be between -1 and 1, okay? And then you would define some bins, basically, and you would say, okay, this term, I have one term which is very, I have this term which is very similar to this one, actually it's the same, or this one is very similar to this one. And so you would add a +1 in some bins for this model. And so roughly speaking, the statistics of the model would be some histograms on the similarity between some query term and some document term. Then you use a feed-forward neural network. And at the end, you will have what they call a term gating network. And this term gating network was just to enforce the IDF effect, basically, saying that if you have a term in the query which is more discriminative, this should be reflected in the aggregation of score. Yeah, so that was the first one of the first interaction-based model that got state-of-the-art result at the time. And I think 1 year or 2 years after, there was this following paper called KNRM, and the title is End-to-End Neural Ad Hoc Ranking with Kernel Pooling. And this paper actually is an extension of DRMM, but it tried to solve some of the limitation of the DRMM paper. And so the main weakness of DRMM is that it's not an end-to-end model. You are not learning representation for queries and documents because the word embeddings are fixed. Okay. So that's the first thing, and the second thing that they show in their paper is that actually the word-to-vec, they are not optimal for the ranking task. So what they propose actually is to have a model where you can actually learn also embedding. Okay. Now, if I come back to this model, to the DRMM model, because you have this binning and this histogram, this part is actually non-differentiable. And that's why one need to change a bit the architecture to make it work. And yeah, okay. So I think this model is very interesting because that was the first end-to-end neural IR model. It also got some nice improvement over the DRMM paper. And yeah, okay. So now I will explain a bit how it works. So, oops, I had a bug on Microsoft. I'm restarting, I'm sorry. Okay. Is it okay? Okay. So you would start with first an embedding layer. Your query terms and document terms would use the word-to-vec embedding as initialization. Then you would compute what they call a translation matrix, which is just an interaction matrix. Basically, it's the similarity between a query term T1Q and one of the document term. And instead of hard-coding some discrete bins, they actually use some Gaussian kernels to capture the fact that some similarities are higher than some others. So what they define actually is a set of Gaussian kernels. And once basically these values in this interaction matrix, they would go to one of these translation to this kind of Gaussian kernels. And for each of the kernels, then you will have a sum or a pooling operation to aggregate the statistics, and this will go to your final score. So if I go back on this equation, first you would do some embedding, then you would compute the interaction matrix, the distance between two query terms and document terms. Then this value would be rough probabilistically assigned to a Gaussian kernel here in this line. Then you would gather the statistic on this kernel for all the words in the document, and then aggregate the values of this kernel in what they call the soft TF features. It's some kind of soft counts, basically. And then your model will basically learn different weights for the different kernels. Okay. Yeah. Maybe it's a bit complex to get all of it, but really the idea is to well, I think to count exact match basically in this model, but also counting terms which are close to each other in the word2vec models basically. And so they did learn this model on a large set of data, and they also show that actually the word2vec models, the word2vec embedding were not optimal, that you would need also a large amount of data to train such a model. Okay, so that's it for the first part of this talk on neural IR model before the pre-trained language model. I think the important idea are the distinction between interaction-based and representation model. It's important to know about the ranking loss to train the ranking system. We have seen the DRMM and KNRM model. There exist much more models such as PACA, an extension of KNRM. I won't cover this because we won't have time to do this. If you are interested by some libraries to play with these old models, I will recommend the Matju library, but also you can find some of the model implemented by different people as well. Okay, so now let's move to the BERT part of this talk, and we will see in this first part we will see also how we can change the ranker with the BERT model. So. But before explaining BERT, I will need to talk about attention. And as I understood by Nicolas, none of you have seen those kind of models before. So I will give my best to explain this. So there is this word attention that you will find in many models now. Both in computer vision, natural language processing, and this attention mechanism is at the core of those pre-trained language models. And it is really something that changed the way we do neural network. So I think it's important to understand this. So first, I will give a bit of a story about attention mechanism. So attention mechanism were invented at the beginning of the year 2012 or 14, I think, I don't remember exactly. And it was invented for neural machine translation. So before, people were doing neural nets, and they were trying to compete with statistical machine translation system, and they were not having good results or better results. And because they invented this attention mechanism, they were able to outperform basically the traditional machine translation system. Okay, so that's for the context. And now, what is attention? What is the attention mechanism problem solving? So if you had a sentence like this, okay, and you had an encoder. So if you want to encode that sentence, what the models they were doing before, they were having a single representation for this sentence. So basically, you have some embedding, a CNN or whatever, and you would do, for instance, a sum or an average of the embedding of the representation for each word. And this is not a good idea, basically, because you have a single representation for all sentences. And so what the attention mechanism is actually, it's a way to account for contextualization, basically. It's sort of a retrieval system at the same time. So let's say we want to translate these sentences, and we are at the beginning of the sentence here. So we don't really care about the global context or the global representation of the sentence. We want the system to focus maybe on the first part to translate. And so what attention mechanism is doing is saying, okay, I'm at the beginning of the sentence and I have a vector that represents the beginning of the sentence. And now I'm going to query this sentence. So I'm going to do some similarity between a token here and all other tokens. And my representation would be a linear combination of well, my new representation will be contextualized with my query. So if I take John as a query, well, I want to pay attention to the terms that are related to John here. And so I will combine differently those embeddings for different words. And so this thing is very important because now for the same sentences, you can have not only a single representation, but contextualized representation, depending on which aspect you want to focus. So it's something flexible and it models context, as I said. Maybe it's not very clear what I said. I don't know if you have questions on this.
Any questions, guys? Did you hear before about the pension?
It's like a sword, right?
Yes, then they will become transformers.
Yes. Yeah. So after that, there were a lot of different work of attention mechanism trying to improve it. And actually, what BERT is a special, I would say, it's a special neural network models that use something called self-attention. I will explain what it is, and that use a special attention mechanism. And so BERT was a paper published in 2018 by Google people. It got a best paper award in some NLP conferences, and it was really an impressive performance at that time. So, so here I put a table that they had in their paper, and so it was some kind of question answering data set, basically, or machine reading. And you see here, you had the human performances here, the F1 around 91. You had the traditional neural network at that time, using some kind of RNN approaches that reached around 88%, 88 F1. And these people, by just reusing a BERT model, by using this BERT model and applying it to these problems, they really had much better performance and things. So this was really a game changer in the NLP community, because it was the first way to encode sentences that could transfer to other tasks and other domains. Yeah, okay. So now I'm going to explain how the transformer is trained and how it works. So the most important task in transformer model is called the masked language modeling task. And so the idea is you take a bunch or a collection of sentences and documents, and you would randomly mask some words, okay? Then you would feed that to your transformer encoder, and then you would have a classification task on the BERT vocabulary, which is predict which word it was here, okay? And so this is, the model is able to do that because it's going to use some attention mechanism inside, some self-attention, which would the model would be able to have some contextualized representation, and that's why it's working well. Okay. So that's the traditional BERT diagram that you would see everywhere. So we've seen the masked language modeling task here. so the first BERT model was using actually two sentences as input. You have one sentence A and one sentence B. And so the model was trained to predict some masked token, but also to decide if a sentence A and B were consecutive. That's called the next sentence prediction task, basically. This is not really important, but you would find it in many papers. Something particular about the BERT model also is that you add some special kind of tokens in your input. So here you have the CLS token. CLS stands for classification. You will see why after. And you have also a separator token between the two sentences. And so what you do with your BERT model is actually you pre-train this model on a large set of documents. And then once you have your language representation, you apply your model to different NLP tasks, such as name entity recognition, some question answering. And to do that, basically, you have either you reuse some of the tokens and output of the model that you fine-tune to solve your task. Okay. So now, if you really want to understand transformer, I would recommend going to this blog called the Annotated Transformer. And actually, I will just
Probably we will screen sharing.
yeah. Can you see screen sharing? Okay.
Yeah, now we see the blog, I guess.
You see the blog, okay. So this is a nice blog to really understand the transformer model. I won't cover all of it, but if you really want to understand how it works, you should have a look at this blog, because it really goes step by step to understand how attention works and how this model works. So this actually is an encoder-decoder model for machine translation, but for the BERT and the transformer model that are important in this talk, I think only the encoder part is interesting. And maybe I would just say a few words about the attention mechanism, which I think is maybe the one important thing to understand for this transformer model. So the transformer model is a traditional feed-forward network, but
Can you zoom a little bit in?
Yeah. Okay.
Okay.
Yeah. So the transformer is a traditional feed-forward network, but in each layer, you have also an attention layer, basically. And it means it is said to have a self-attention mechanism, meaning that the attention is in the encoder, meaning that each token, each input token would pay attention to all the other tokens in the sequence. So what it means is that for each token, you're gonna embed it as a query. You do linear projection as a query, and you would compute some kind of some distance to all the other tokens in your sequence. Okay, and once you do that, you would this is done by this projection Q and K. Once for each token you compute some kind of similarity to all the other tokens in the sentences, you would then average those representation to get a contextualized representation. So that's how the self-attention works in the transformer. I think, well, it's not really useful that I spend time explaining this in this lecture, but I would encourage you to understand this. I think if you do study things in IR and in artificial intelligence, you will need to understand this mechanism. Okay. Okay. No, so sorry. Okay, let's see. Okay. Can you still see my screen, right? Yes.
Yes.
Yes. Okay. Okay, so now we'll speak a bit about information retrieval dataset and task. So you have known of these track challenges, and there was this track deep learning track, which is based actually on a collection called MS Marco. MS Marco is a collection given by Bing, by the Bing search engine. It's a set of web queries with some given passage and document. It has, I mean, the MS Marco has some limitations in terms of annotation at training time, but using the track annotation is the, I would say, is the standard way to benchmark those models, basically. And so if we look very quickly on those datasets, for instance, you see some queries which are very easy for BM25 models, such as this one, where lexical match is really important. So if you use BM25 on this query, you find this document which is relevant. Okay. If you, but if you enter more difficult queries, such as why did the US voluntarily enter World War I, what BM25 give you is this document, basically. I know it's complex to read here, but things where BM25 does not work is because, I mean, you have some typo, you have some vocabulary mismatch between enter and maybe join that somebody can find in relevant documents. And basically on those documents, BM25 is not giving us the right answer directly. Okay, so now coming back to BERT. So how can we use BERT for IR? The simplest things to do is to basically learn a re-ranker. And how we can do that is to simply use BERT in the simplest way it was done for as in the NLP community, is to fine-tune the model on some annotated data, where you both input the query and the document. Then each token would pay attention to all other tokens. At the end of the model, you will get the representation of the CLS token, which is the classification token. And then with this classification token, you decide whether the match, I mean, this representation is the representation for a relevant document or irrelevant document. And so you simply do a cross-entropy loss of this. You fine-tune your model on some annotated data. And that's the way that's the way you can train a re-ranker with that, basically. And so we were the first to do that. That was the Noguera and Shaw paper in 2019. And they actually had much better performance compared to previous model. So if I show a table from this paper, let's focus on the MS Marco collection with this metric, which is MRR at 10, which is a metric that I guess Nicolas doesn't like, but that's the official metric, unfortunately. So you see the BM25, you see the KNRM models here that I talked about before. And so the KNRM and extension were at much better performance than BM25, which was around 16. And you see that simply fine-tuning a BERT model, you had already a huge boost in performance. Okay. Same thing on other datasets. And so what we saw actually at Trek in 2019 was a plot very similar to what I showed in the introduction of this lecture, is that, okay, we had some neural net, a lot of different neural net, neural IR models, which are good. And then we see the first pre-trained language model or BERT model getting better result compared to the traditional model. Okay, so we had huge gains with this BERT model. Now I have a question for you. The BERT re-ranker, is it an interaction or a representation-based model? I can show you this again. Any opinion?
Flip the coin, guys.
What?
I was suggesting to flip the coin and decide.
Yeah.
Yeah, in that. So there is no scoring here.
Okay. Okay. No opinion? So I would say actually it's a bit of both, right? Why? Why is it an interaction-based model? Because basically each query token can pay attention to a document token, and they can get some score as well. They can contextualize themselves. So it works a bit like an interaction-based model. But nothing guarantees you that in your model, actually, you use some cross-attention between these. Maybe the model works by doing a representation-based model as well. So to me, it's kind of a tricky question, but it's interesting to think about it, but it's a bit of both, actually. Okay, so that's a huge gain, but the problem with this big model, with the BERT model, is that it's very costly to compute. It's very slow. You need to use GPUs, and if you do re-ranking, you need to apply BERT to each query and document pair, basically. So depending on the conditions that you have and the re-ranking list that you want to do, it can be 2K to 10K more slow than using BM25. So that's why we need a more efficient model. And this is why people have researched different approach to solve that issue, basically. Okay, and I'll do a small parenthesis here on this BERT score paper. You will understand why in a few slides. So we have seen that in the BERT re-ranker, we use cross-attention to capture some relevant signals, basically. Well, actually, in the NLP communities, they have developed this metric called BERT score, which was shown to have some benefits over the blue evaluation metric in machine translation. And the idea of this is to use BERT to compute some similarity between sentences. And how does this work? So you would take one sentence, the weather is cold today, and it is freezing today, okay? You would feed that to your BERT model, get a vector for each token, and what you will gonna do is to compute, again, an interaction matrix, basically, saying, okay, this token will compute the similarity with this one, and this one, okay. So what they do, basically, is to use BERT, then you compute an interaction matrix, and once they have this interaction matrix, they compute two things. One thing which is called precision and recall. Basically, for a line here, you will take the max score for each rows, okay? And I think that would be called the precision. And they also take the max for column also. And they would call that the recall. And they would combine this into something that is very similar to F score, okay? So that's another way to compute some similarity between sentences. This was developed in the NLP community. You can find it. And why I'm talking about this? Actually, because one of the popular models now, which is called Colbert, published at CGIAR 2 years ago, actually use a bit this idea. So how does it work? You take a query in a document, you compute some representation independently, and once you have your query and document token representation, you're gonna do, again, an interaction matrix. You're gonna say, okay, for this token, I'm gonna take the similarity, the maximum similarity with all document token. And once I have this maximum similarity, I would sum this. So this is basically captured by this formula, the similarity between query and the document. It's a sum over query terms of the max similarity between the embedding of the query term and the embedding of the document term. In practice, it's a cosine because the embeddings are normalized and there is a projection matrix. Well, so this is interesting because I think this looks like a TF-IDF formula, and but it's based on embedding computed by BERT, basically. Okay, and so why it's also interesting is because first it works very well. So you see here again this metric, this MRR metric at 10. Here you have the query latency. So if we just look at the performance here in terms of is the model able to learn a good ranking? So the BERT model are around 36 or 35. And basically with this Colbert model, you reach the same performances as this, meaning that you don't need a complex cross-attention mechanism between query and document. A simple interaction matrix can do the trick. The second interesting thing about this model is that actually it's way faster than BERT. Why? Because now that you have a representation of the query in the document which are independent, then you can pre-compute this for the document. For the query, you do that at runtime. And it means that at runtime, you only need to go into the query encoder and compute this interaction matrix here. And that's all you need to do. And that's why it's faster. Nevertheless, there is one problem here, is that you don't see it in the query latency because it doesn't show disk space, is that instead of storing one representation for one document, you need to store a representation or one vector for each token. And it's okay for small collection, but for big collection, it can be challenging to do this. Okay. So I think that's it for the BERT part. We have seen quickly what was an attention mechanism, what was the mask language modeling task. I gave a very quick introduction to MS Marco, the BERT ranker. I think there is the issue of efficiency with this model, and I quickly explained the Colbert model. Are there any questions on this part?
Any question also at home, and also people attending on YouTube can write in the chat of YouTube, and I will pass the questions to Stéphane.
Okay.
I have a question.
Yes.
It is on the data used for training the Naver models. So which kind of data are used in training and which kind of data are used for testing?
Okay, good question. So, again, Microsoft crashed. I'm really sorry. It restarts again. So the way people go is usually to train on the MS Marco collection, and it's a big collection which has some annotation. I mean, for one query, you have something like 400K queries, and you have one relevant document on average. I mean, 1.1 relevant document for that query, and people test on the track 2019 to 720 data set. That's one way to benchmark this model. Okay, let me share again. Okay, I guess you see my screen now. I hope Microsoft won't crash. And then there are also other collections such as robust people also try to see. I mean, there exists a lot of different collections to test this model, but I would say that the one of the most important one would be the MS Marco and the track collection to do this. Yeah. I'm really sorry. That's the first time that Microsoft crashed for me. Okay. Can you see my screen?
Yes.
Yes, yes. Okay. So now let's move to the last part of this talk. I mean, is there other questions or no?
Yes, there is a question in the class.
So how much time does it require to train a BERT model, and which GPU, I mean power, do you require to train it in a fast time?
Mm-hmm.
Did you hear it well, Stéphane?
Yeah, so the question is how much time do we need to train a BERT model and how many GPUs to do that, right?
Yeah.
So for the BERT model, I would say everything depends on the batch size and the sequence length that you take. I think you can train on good GPUs with a small batch size. 1 or 2 GPUs for learning a re-ranking, I think a re-ranker, it's enough. The same thing with Colbert. Typically, you can train this on 2 GPUs with a batch size of 32. And how long? To be honest, I don't really know. I would say in a few hours, you can train a Colbert model, basically. Because there is also one thing that is not explained here is that, okay, you take this pre-trained language model, so you train them on triplets, then you need to index the collection, which also takes some time, and then you can do the retrieval. And for indexing the collection, you need I mean, you have 8 million documents, basically, you need to go over all those 8 million documents. And depending on the model, this can take some time. I mean, this is for Colbert, but for the re-ranker, it's a bit different. So I'm sorry, I don't really answer your question. It really depends on some hyperparameters such as batch size and sequence length and the time you want to train. Okay. But yeah.
Thank you.
Okay. Okay. So I'll move to the last part of this talk, which is learning a first stage retrieval. And so in the previous part, we've seen how to change the re-ranker. Actually, Colbert is also kind of a special first stage retriever. I won't go into the details. But in this part, we're going to see how to change the first retriever. Because people have seen that, okay, we can change the re-ranker and get some boost. Okay, let's try to change this now, the BM25 model. And so the BM25 model is something, I guess you had a lecture on this. It's an old model. It has really stood the test of time. It has been the backbone of search engine for several decades. And it has been a recurring question if we can replace actually this model by something learned with machine learning. But for years, this thing basically didn't work. I think it was something very difficult. Yeah, so I mean, there are no limitations about BM25. You know, the assumption it is based on are not really completely realistic. Anyway, nevertheless, the model has really been able to resist any other model, basically. And now my question to you is that, okay, you've seen some of the things in this lecture. Do you have any ideas of how you would learn a first stage retriever? How would you replace BM25?
We could use a term frequency vectorizer and use a a neural model, for example? Could it work?
Okay.
Also, language models can be used instead of BM25.
Yes, you can use language models instead of the M25, but this is always probabilistic ranking as the M25.
Yeah.
The question is more if you want to put at work this neural stuff as a first stage retriever. How do you do that?
Okay. Well, I think it's interesting to think about this because I think I'm a bit late on time. I will continue. Okay. So we're going to see one of the main approach, which is called Siamese or B-encoder model, and then I will present a collection of sparse model. And if you have time, I will talk about the BR benchmark, but I'm not so sure. So the way people have done this, I mean, trying to replace the BM25 model with a BERT model, it was done by a Siamese or B-encoder first stage ranker. So the idea here is to compute a representation for the query or the document independently from each other. In the BERT re-ranker, you had to concatenate these two things. And once you feed this query and this document into BERT, you get a representation at the end. You do a mean, for instance, a mean of the token embedding. You have this representation here and here, and you can simply do a dot product or cosine on this. So that's the way people have done that. Now, one implication of this is that you cannot use anymore an inverted index to do the first stage ranking, because now you need to index some dense vector, okay? A vector of, you have a few hundred dimensions, and you know what people use, basically, they use what has been developed in the computer vision community, some library on approximate nearest neighbor techniques. Okay, so that's how you can do that. Then you have many way to train this model. People have paid attention to the negatives they use to train this model, because, for instance, you can start from a BM25 model and take a positive and a negative provided by BM25, but the negatives provided by BM25 may not be the best to train this dense and B-encoded model. Okay. If you want to start with this model, you have the Hugging Face Transformer library, but also the sentence burst library, which is very good. I had prepared a small notebook, but I think I'm late, so I won't go with this. So basically, if you look at this library, you can just follow the tutorial and download the model, run it on your machine, and compute some embedding on this way. Okay. A second important thing to know about this model is how they are trained. So I spoke about negative, but there are also important techniques that is useful to know to train this model. It's called knowledge distillation. So knowledge distillation was invented to basically first compress big neural network into smaller ones. So this has been applied to, for instance, transfer an ensemble to a single neural network or just making smaller model. But here, in our case, it can be used in a smarter way. It can be used to transfer the re-ranker knowledge to the first stage ranker. And how do you do that? So you first train your BERT re-ranker. Okay. Once you have your BERT re-ranker, you use the re-ranker to score some positive and some negative documents. And those scores, they will become the new ground truth for your student model. Okay, so the second step is to train, for instance, your Siamese or B-encoder model. to predict the same weight as your re-ranker model. And when you do that, you kind of transfer some kind of the knowledge of the re-ranker model, but you also correct the annotation problems or the missing annotations that you have in your triplets. Because on many collections, you have one document which is positive, and sometimes the document is negative, okay, but it has not a score of 0, basically. It is close to the positive in some sense. It's moderately relevant, but it's not annotated. Okay, and so that's what people have used to improve the performances of such systems. And there are many variants on the loss that you use for distillation and the way you do it. So I won't cover this. Okay, so now let's get back to this this debate in IR about dense and sparse or interaction or representation-based model. So now we have seen that dense models are really much better than the sparse model. And for curiosity, like one of the research questions that people had was to wonder whether they could learn a state-of-the-art sparse retrieval model. And yeah, you could say, okay, why should we learn a sparse retrieval model? I mean, it can be fine with the dense retrieval model. Well, I think there are several reasons for that. We have a lot of work on IR theory that shows that the lexical machine signals are important. We know that there are some good properties about the sparse model. The sparse models are interpretable because you do some explicit matching at the word level. Recently, it has been shown also that some dense retrieval models, such as the Siamese, had some generalization issues. Maybe, well, I won't have time to talk about this. Anyway, there is also the fact that if we analyze, for instance, the Colbert model, we actually see that the model is kind of learning some exact match behavior for some terms and more semantic match for some other. So maybe it would be just interesting to try to learn a sparse model directly. And that's what the model, several people have tried to do that. Recently. And the first paper that tried to do that was this model called DeepCT. And the idea is to use a BERT model basically to predict some term weights that will be used with BM25 at the end. And so the pros of this model is that, okay, the inference times will be very easy. It will be as fast as BM25, basically, because all the computation cost would be at indexing time, okay? And what they propose to do is to, okay, you have the BERT the sentence here, you have some BERT model, and for the word goldfish, basically you want to predict some weights like this, such as 0.87. And how they did that? Well, they pose this as a regression problem. For each term that they have in a training collection, they're going to say, okay, this term, I'm going to measure query term recall, and this system is good for this query. This value should be high. So this kind of the Y variable, basically. This is your target. And what they do essentially is to plug a BERT model, have a projection layer so that you predict some regression weight for a term, and then you use BM25 in your retrieval system. Okay, I'm a bit late. The second approach will be a model called doc2query, and in this idea is really to reuse the sec-to-sec model. So the same thing as a translation model. So you take a document, you input a document, your document, and then you ask a model to predict a query for that document. So here you have something that talks about cinnamon and blood sugar level, and you get the output, there's cinnamon, lower blood sugar. And once you do this, you do it several times, you add this query to the content of your document, and then you use a traditional term-based model such as BM25 or any other model. And again, this means that the model at runtime will be very fast. Okay, so that was the main idea of this doc2 query model. So you use a sec-to-sec model as if you were doing machine translation, for instance, from French to Italian, but instead you translate from the document language to the query language. And it's a bit like in the language modeling approach. Basically, you try to estimate the probability of the query given a document. And actually, this thing, I mean, this idea of using kind of a translation model, it's actually old, very old. It starts like end of the 19s, and where people use at that time a word-based translation model to do this. Yeah, so some results on the MS Marco collection. So you have BM25 here. You have BM25 with total relevance feedback, which doesn't work in this collection. But now if you use doc2 query, then you get some boost over BM25. But basically, you are really far from the performance of the BERT model. Okay. So there was some extension of this doc2 query model with a model called doc-T5. And the main idea is used to actually reuse a better pre-trained model to do that, a model called T5. There is a model available in Italian on the Ginface. I had prepared a notebook on this, but because of time, I won't show you how it works. I mean, if you can just follow this, you'll see what the model is doing. And again, so if we compare some first ranker, we had so BM25, doc-T5, the standard Siamese BERT or B-encoder model, and the model called task balance, which is the same model as the Siamese BERT model, but trained with hard negative manning and also distillation. And so you can see the different level of performance on the MS Marco collection, but also on the Trek collection. So you see that the simple doc-T5 already gets some boost, but very close to the Siamese BERT model. And then properly training those models is really important. So having good negatives and doing distillation is clearly important. Okay, I have 5 minutes left, right? Yeah. So okay, and so I'm going to say a few words about SPLADE, which is a model that we did. I won't go into details, and then I would try to summarize what we said. Okay, so SPLADE is a model that we did at Naver Labs Europe. And one of the main differences between the previous sparse model is that we have a controllable sparsity, and we can really adjust the efficiency and efficacy trade-off. And how that it works, it's actually very simple. So as the other model, it will use BERT, but the main difference between this model and all the other models is that in BERT, there is a layer called the MLM head, which is kind of the logits to predict a mask token. And what we do in this model is to reuse this head instead of throwing it away. So for each token, we predict some probability of another word, basically, okay? And we put some sparse regularization on top of this, because if you have frequent word, for instance, you always predict a frequent word with your BERT model. If you do that, you will hurt the latency of your retrieval system. So that's why we need some sparse regularization. Okay, so that's the main idea. I won't go into the slide and the technical explanation because I'm out of time. One important thing I would say is this: we use a flops regularization to basically count the number of operation that you had to do if you have to use inverted index. So the main idea is really to penalize the frequent words, so that when you compute a sparse representation, you don't have a huge posting list. That's the main idea. So I won't go on those details. I'm sorry. One nice thing about the SPLADE model and other sparse model is that actually you can look at the predictions. So here you see a document. What strikes through are the words that the model decided not to use because they are not important for that document. And also for this, you also see that the model has predicted some new words. Sometimes it has some stemming effect that you see in green and some expansion terms in red. Okay, so I think I won't go into the results that are not important. Let me summarize what we've seen in this part. So I've talked about the first stage retrieval. We've seen the Siamese and the encoder model, the DeepCT, and the sec-to-sec approach. I gave a very rough introduction to the SPLADE model. There are other sparse models. I won't talk about this. I wanted to talk about the BERT benchmark, but I won't have time either. I think there are some challenge in this field which are related to the evaluation of these models because the collections are becoming harder to use. For instance, last year at TREC, the collection was not reusable because the model found too many positive documents. There are some issues on the generalization of robustness of this pre-trained language model. So if you had a typo, if you change domains, maybe some of the models that you have trained, they don't work very well. The last challenge is also to understand actually what those models are doing. It's not totally clear. Okay, let me skip those slides about the BERT benchmark. Finally, okay, if you are interested by some kind of research question that the people that the IR researchers are looking at, I would recommend this paper by Google people about rethinking search, and they try to show that a different way of doing IR is possible with this model. Okay, let's keep this. So let me summarize what we've covered in this lecture. So I spoke about neural information retrieval before the pre-trained language models. We've seen the DRMM and KNRM papers. Then we saw the BERT re-ranker and the Colbert model, and our attention was important for this model. And then I spent some time on the first stage model that tried to replace the M25. And for this, you have the different models listed here. And so I think we've covered the history, the recent history that happened in IR in these recent years, from the first neural information retrieval model to the recent pre-trained language model for IR. And I think, yeah, so we've seen this, and I think that's it. I would like to thank you for your attention and your question, and sorry again for the PowerPoint text. Now, if you have more questions, I will be happy to take them.
Thank you very much. Any questions, guys? Curiosities? I have a question.
Yeah.
Are you open for internship, these kind of positions? At which level?
Yes, we are open for internship. We have many internships available. What is complicated for us is that often the interns, they always want to come at the same period, which is like spring and summer. And at this period of the year, we have some limitation. Outside of this period, we have no limitation of having interns.
Okay. And then at master degree thesis level or just PhD visitors?
We have both. We have both actually. I think that for master thesis also it depends on the time because 3 or 4 months may be too short. Well, I don't know. This can be adjusted on the topic and the team. So
For us, the master cases can be up to 6 months, basically, to a whole semester. So it's a little bit more.
Yes. So actually, we will have some internship soon. The thing is, there are a lot of competitions for this internship, and so students have to be quick to reply, because it's a lot of people are applying, basically.
And that's very good to have a bit of competition.
Mm.
Any questions, guys? Anything else you would like to know? This is really the frontier of the research in the field. Okay, so thank you very much again, Stéphane, for the very interesting talk and for your time here with us. And I wish you a nice day and possibly good lunch.
Thanks, and hope to see you at CGIAR. Okay.
Oh yeah, for sure.
Okay.
Bye.
Bye.